Hello and welcome to this third event in the series of machine learning lectures um, run by Google Crowdsource along with Google AI. In the previous lectures, we explored the outlines of machine learning in its broadest sense. We looked at some topics, we broke down some concepts, and we didn't quite get onto coding yet, but we looked at several simulations of what machine learning programs do using the TensorFlow playground, which is available on TensorFlow's website, and also looking at several kind of thought experiments and other material provided by, for example, Oxford University. And today we're going to go a little bit further. We'll start off by looking at some more terms. Then we'll move on to some case studies and one technical term. Don't worry, it's not too much. One technical term. And then we'll end by doing a little bit of computer programming to illustrate what this technical term is and how it's used in machine learning. And we'll do that in R, the statistical programming language. And if we have time, we'll do it in Python. This is actually one of the shorter lectures, so this should only take about an hour. And it's being recorded, so feel free to drop out and we will send a link with all the materials to you. Okay, so recapping where we were previously. What is machine learning? Well, I think we concluded that machine learning is not as distinct from other methods and practices of statistical inference that we know from high school or university. It's just another way of looking at data and making conclusions from data. The big difference is that that we have a process for iteratively improving our way of modeling the world. And in that sense, the real task of machine learning is to try and understand why certain outputs happen, certain outputs from certain inputs happen, rather than merely deriving those outputs. And I think that one of the most insightful, if simplistic ways of viewing it, would be to imagine that normal mathematics and statistics is concerned with having a function, an input goes into the function, and then your objective is to find the output. With machine learning, we have the input and we also have the output. And our mission is to find the nature of the function. So if you imagine there are those three sort of variables, input, output, function, the normal scientific inquiry is to have the input, try different functions, and look at the outputs. Machine learning is to have already the inputs and the outputs and try and derive the functions, if that makes sense. Okay. So we'll look at some definitions, other definitions, alternative definitions. Machine learning systems take inputs, data, to make useful predictions and decisions about previously unseen pieces of data. Now, this sounds like a very anodyne and generic way of describing statistical study. But what you want to look at here is previously unseen. Those are the two key words in my estimation, because this speaks to the essential division in machine learning between procedural division between test and training data. So early on, and this is something we'll see when we actually implement this, you split up your data into training and testing. That is one of the key distinguishing features of machine learning. Generally speaking, very generally speaking, you want 80% training, 80% of your data for training, and 20% for testing. That's your rule of thumb. If you have a very large data set, it's customary to use less testing data. So 100 million values for your whole data set. If you split it up 80-20, you will have too much testing data, probably. There are instances when that is not the case, but but generally speaking, you want 80-20 or less than 20 for testing. And the previously unseen bit here, sorry, to recap, previously unseen just means the testing element. So you've got your model, now you test it, then you iteratively improve it. Another definition. Machine learning is a specific field of AI where a system learns to find patterns in examples in order to make predictions. Okay, so similar kind of message. What it's specifically talking about here, I think, is the division between supervised and unsupervised, where supervised learning is concerned with applying existing understanding of the data to the process of splitting the data and then building a model, fitting it, and then testing it. Okay, I think we'll go into that momentarily. Between supervised and unsupervised. Supervised, sorry, is where you don't have any such presuppositions. You go in with very little information about your data. And this is very useful for unstructured mass of data that you have in, say, social media, where it's very difficult to categorize, but there's such a multitude of it that it is possible to draw insights and clump things together in a process that could be called feature engineering. You're essentially trying to find categories, or you're trying to find columns, if you think in a sort of tabular way. Machine learning systems might, oh, sorry, we didn't read this one. Computers learning how to do a task without being explicitly programmed to do so. Right. So explicitly programmed in this sense means that from the outset, you gave it instructions of what to do in a sort of contingency, but you didn't do so in a specific manner. You simply said, here is the data on which to train the model, and you should be able to adjust this data based on the performance of the model. And as we'll see later, what happens is that the accuracy of the model improves as it runs through the test data. And what it means here, being explicitly programmed, is that you can, once you've done the initial programming, you can, in a sense, let it improve itself with the testing data. Machine learning systems might label or classify data, predict numerical values, cluster similar pieces of data together, infer association patterns in data, create complex outputs. Yeah, sorry, I should have like vocally said that differently. I should have said infer association patterns in data and create complex outputs. So you can sort of see here, although this looks like a very disparate group, it's characterized by more or less what we've been talking about, which is having, as it were, a function input, function output, and allowing the function to evolve as the inputs new inputs are provided and outputs are studied. All of these can sort of fit into that category. Okay. Why or why not? Now it's telling us to look at some news. Why or why not use machine learning? So it's got an example here, which is automating drone-based wildlife surveys saves time and money. A lot of the questions in this session are going to involve what an economist would call opportunity cost, which is to say, we can do machine learning on almost anything. Any sort of data which we can collect data on anything, and on any data we can perform something like machine learning. but is it efficient? Your first, your first question should be, how much is the computing costing me, and how much is it, um, how much less is it going to cost me than it would even a year ago? And by virtue of laws akin to Moore's law, which the of computing power and the power were would uh, the cost would go down and the power would go up exponentially. By virtue of things like that, we've been liberated of part of the concern for machine learning, which we've had access to since the 1970s, versions thereof. We've been liberated of the question of, can we do this? In most cases, we can do it. In some cases, we can't. And in a lot of the questions that we encountered last time with regard to deep learning, the computational difficulty is, in the lingo, NP hard. So it's something that is exceedingly difficult with anything short of a quantum computer, because the possibilities are so vast, and when you're dealing with sort of any prediction is probabilistic. So probabilities, calculations on probabilities can quickly spiral into impossibility almost. I said this last time, and I'll say it again, which is that when you're dealing with networks, as we often are with machine learning, particularly with neural networks, you get a sense of the difficulty, because famously in his book, The Human Network, Matthew Jackson wrote that in a class of 30 students, you have more combinations of friends. So one student with 0 friends, or one student with one specific friend, or another specific friend, or neither, or one of those, or both. You have more combinations in that classroom than you do atoms in the universe. You can imagine quickly. Was it 30 or was it 100? Okay, well, you get the sense. As a normal classroom can contain, just by looking into this calculation, you can see that any amount of computing power quickly falls short of what is necessary to do. So your first question is it computationally possible? Would a traditional programming solution be more efficient? That's kind of asking the same thing. You would, if you had all all else equal, you would probably prefer a machine learning program, because you can kind of step back. It's automated. So, traditional program is usually quite labor intensive. If you've ever written a program, what you'll discover is that the syntax is very arduous, and the solutions can often be distorted by the tiniest error. Even with modern IDEs, which is developer environments, you encounter an enormous labor shortages, labor difficulties, which is one of the reasons why machine learning, one of the chief tasks of machine learning now, is automating programming. So a lot of machine learning is actually being put into making programming faster. And if you're interested in this, you should check out an initiative called the GitHub Copilot, which is that you can't sign up for it at the moment. You can go onto a waiting list. But what it does essentially is, when you're writing your code, you give it a few prompts, and it essentially writes the whole of the code for you. And having seen it in action, having used it, I can tell you that it's transformational. A developer could potentially save 50% of their time. But of course, the closer we get to 100%, the more nervous we are, because 100% is redundancy. So this is really where automation counts. So for a traditional solution to be more efficient, the irony is that traditional programming is now increasingly to do with ML. So it's very difficult to do traditional programming without machine learning now. If you were just sitting there with your keyboard typing out all of the commands with no prediction, it would be very time consuming. So would a traditional programming solution be more efficient? Probably I would say at the moment, almost certainly no. Could a human perform the same task in less time? So this is really a question about an economic concept called opportunity cost. Could a human perform the same task in less time? You're really asking, what is the value of a human's time? A machine doesn't want to get paid. You have to pay the electricity for it. But if it's been automated and it's running, it's essentially zero cost. So how valuable is time? I'm assuming there that there are very few things that humans can do that machine learning can't approximate. Of course, fine art or something of that nature, but is not only very difficult to imitate, but would lose its value if imitated. Although that having been said, there are now AI artists. If you want to check that out, there are actually AI artists who have sold their art. Although to me that sounds gimmicky. But increasingly, you have to look to areas which are unautomatable by principle. So things like aspects that only have value because they're associated with an identity. And that's the whole notion of identity ethics and digital identity. If you're interested in that topic, there's actually a very good report and training course issued by the United Nations Commission on Trade and Development, which is called Digital Identity. And that gives you a great overview of this issue, which is intrinsically now tied to this. Could humans do it better? Or could they even do it at all? Or what is the value of humans doing it? What are the economic implications? Okay, number 3. What are the benefits of a machine learning model in these instances? Okay. I didn't describe any instances. I think when this course was designed by Google AI, and obviously they are the ones who are interested in it being delivered now, they very much wanted this to be done in person, and so you would be finding these news items, and kind of analyzing them for their kind of breaking down the journalism of it. So a lot of sense of exploring machine learning, this course, in fact, is exploring the interpretation of machine learning. Let's move swiftly. Okay, so here's our friend, supervised and unsupervised. If you want to reflect on supervised and unsupervised, one thing you can simply say is supervised is you have some suppositions, you have some prejudices, if you will, and unsupervised is no presuppositions. You guys seem to have a mass of data and you try to find patterns in it. Your algorithms are there to find patterns in unstructured data. Those are the unsupervised ones. And then supervised, you have paired data. And to pair data implies that you already have columns, right? So it's not just that you have paired data, it's that you're already coming to this with, as it were, laid out, or the data's already been laid out in some form. With really bad unsupervised data, you might have you might have to really impose a structure upon it. You might have to you really might have no guide at all. You could have huge amounts of text data with limited punctuation, bad grammar. All of your rules that you might want to impose are simply absent. So if you had a huge cache of, let's say, TikTok videos, right? It will be very hard to go through to arrive at a spreadsheet of that information, right? So you'd have to go for your video classification, facial recognition, and this is the genius of these the value proposition of these giant companies like TikTok is not that they have all this video content, or they have all this content. A lot of, you can just scrape the content. And if you're interested in that sort of thing, I would recommend using something called Beautiful Soup, which is a Python package. We may do another session on this, because scraping is such a huge part of machine learning, but I'm actually interested to do maybe a session on this. But you can just scrape all the videos onto your own, let's say, copy of TikTok, scrape thousands, something like Reddit. When Reddit started out, the guys who founded Reddit were literally just reposting things they found elsewhere on the internet. And so that's not the value. The value is that they have this huge mass of unstructured data. They've applied their unsupervised algorithms to it. They found patterns which they aren't going to share. These are private, and they are using these to suggest videos. And I think we're going to talk about this later as a case study. But because of the computational intensity, and the the ingenious methods behind these algorithms and their results, and the length of time it takes to do them, you as a company will derive a lot of value from this. Supervised, you can just sort of copy it. You'd be like, well, we'll just cut it this way, And one of the beauties of unsupervised learning is that even the human might not understand that. So the actual guy doing it might not understand the output. So it might be that the level of the clustering might make sense to the machine, and it's producing your positive results. Maybe it's more clicks or something, by suggesting based on this supposed association. But you look at the association, and it seems to you to be complete nonsense. It hasn't provided an explanation for you. Machine learning doesn't intrinsically come with explicability. It's going to do something, but it doesn't have to explain itself. It's just found a pattern, and you can eyeball the pattern and say, here's the pattern, here's the feature. I'm going to turn this into a supervised model with these features and throw those out. But it could also be that you just don't understand, right? So imagine you but you like the results. It's doing something, and this is a matter for ethicists and all the people involved in machine learning evaluation. Oh my God, don't use that word, evaluation. Evaluation is something we're going to encounter later when we do the process of machine learning. But what you want to think about is how do we look at the results of unsupervised learning, and word other than evaluate, analyze. I don't know. Okay. Oh, here it's giving you some examples. Oh, and you can go to the Crowdsource app. So at the bottom there is a link to the Crowdsource app, where you can try out these machine learning algorithms in action and use them with things around you. So image label verification is supervised learning. Not necessarily, but in this case it is. So it's like cat or not cat. You have a load of so the way this would work is you start out with paired data, image, and then it's cat or not cat, with like a label or tag of not being cat. And then in this verification, what you would have is more data, and it would be images of something along with tags saying cat or not cat. And your business would then be to say, are these labels correct? And kind of what you would want to do is, it's a difficult exercise because maybe the new testing you're doing is more correct than your model. Maybe cats look different, in different parts of the world, and you're consistently throwing up bad examples. So you want to be able to balance that between iteratively improving and also passing judgment. Unsupervised learning. Oh, so this is a very famous example. Semantic similarity. When language models began, natural language processing, NLP, began, the assumption was that languages were rules-based, and dictionaries, thesauruses, any number of books, linguists, etc. And all you had to do was get all the linguists together, write out a proper, complete system. And by complete, I mean that it's kind of end to end. You have contingencies for everything. Rather as you have a programming language. So really just making a sort of mapping on language to programming. And it failed, totally failed. And the reason was that they just could not get down. They simply couldn't get the results they needed. They could never write down enough rules, which is strange because you think, okay, dictionary writes down all the rules. It doesn't. Actually, doesn't write down all the rules. There are lots of implicit rules, and especially when it comes to translation, it's so various. And again, the computational difficulty is so vast when it comes to making a judgment that it failed. And what in the end worked was unsupervised learning, which is basically to have paired data, not paired, sorry, scratch that. You have a translation and you have the original document. And these were often web scraped from repositories, and they were overwhelmingly government repositories because the governments have the highest standard of translation. So think about Canada, which has English and French. Everything has to be in French and English, I believe. And then from that, they just looked at the correlation and they built a model without any presuppositions about what translates to what. So this sounds absurd from the outset, doesn't it? Because you could have an association between cats and collars, because cats are always wearing collars, right? That's more of an image, but you get the idea. So unsupervised learning was deemed to be gibberish, but because of the huge volume that they were able to do, of the volume of data that they were able to input into these models, it actually produced extraordinary results, principally Google Translate. And kind of the message was after that, and this is like early 21st century when it started to get these kind of work really well. The kind of message was that you can have you can have messy data as long as it's large messy data. Big and messy is better than small and tidy, which is not a happy deduction for scientists necessarily, because scientists are pedantic. Okay. Oh wow. So here we're going to deal with later today. Loss. Now, as you can see, these are just very simple graphs with a line of best fit drawn between the points. And what you should be looking at here is whether these are good lines. And of course, how do you work it out? This will be familiar to anyone who's done a kind of least squared calculation in their studies. It's the one which is closest, which has the least distance from itself at each of the dots individually. So looking at this, you would say it's I think it's number 3, but yeah. And now you actually have it quantified as loss. So again, quite a familiar calculation. And you can see that the loss is the least. There you go. Indication. Okay. So let's predict the price of a house. Here are the case studies that we're going to talk about. And what you have on the left are the features. And remember, features. Features are the things we start off with in supervised learning. and they are the things that we find with unsupervised learning. So if you had a supervised model, what you would have is essentially just you'd already have chosen these features, and you'd just be training the model on these features: location, number of bedrooms, size of property, square footage. And you wouldn't care too much about number of light switches or color of house. But you might discover that your assumptions were wrong. Perhaps number of light switches speaks to some larger truth, and it's actually highly relevant, or is the proxy of something that's highly relevant. Color of house. Maybe it could be that pink houses really disgust people, and no one ever buys them, so their price shrinks. It's the sort of thing that if you were deliberately designing a model, you might think totally relevant. But if you are going into fewer presuppositions, you might actually be more sympathetic to. Let me take a swig of tea. Okay, so recommending which video a user should watch next. What do we think? What do we think? Oh, whoops, gone back a bit. This is utilizes a field of statistics or economics called market basket analysis. And the name simply means what do people have in their basket? If someone's going for a supermarket, what are they likely to buy in conjunction with each other? So you go to buying milk, maybe cereal. If you're buying cereal, perhaps you want fruit. I don't know. I mean, I'm not great at supermarkets, but you can see that there's it's like auto-completion on sentences. If you typed something, what's next? Although, a word of caution, actually, that's slightly different because order matters. So if you remember back to your combinatorics training, you'll remember that order is very important to whether you're dealing with permutation or etc. When it comes to texts, you can rely on order to be very important. If you're going into a supermarket, perhaps it's less important. So in fact, it's a rather different process. But this is somewhere in between, because if you watch one video, you're highly likely to watch another one. But is that true of the reverse? No. So order does matter, but not in exactly the same way as texts. So let's look at some of these features. Topic, popularity of a video, number of views, creator of video, and then you have these sort of question marks over length of video, age of video. Are these relevant? Again, what you should be thinking about here is what features would you put in, and then what features might come up in more unsupervised learning. And if you want to study more of this market basket analysis, I'd recommend looking at econometrics, some Python packages for econometrics, which deal extensively with this question of what will someone buy next and what is the probability involved, and there's some very efficient methods for looking at that. Checkpoint on learning. Now you will be tested. A baker would like to optimize pricing of cakes in their bakery, depending on previous pricing, cost to make, and time of year. So, again, we have a sort of economics question here, because the baker is presumably, with these variables, cost minimizing, which, if you remember to your microeconomics training, is optimizing your cost function, I believe. But how might you avoid doing that? If you hate microeconomics, how might you avoid doing that with machine learning? This is one of those instances where machine learning is perhaps less optimal. Because of the way that machine learning learns iteratively and haphazardly, at least in the beginning, and we'll see that the loss function is really big. So unfortunately, unless this baker is very shrewd and he's got his testing data as well as his training data, instead of simply using new information as the testing data, he might be in for some big losses. The benefit to the business would be that you could potentially find new insights. You could get ahead of the curve. Let's say all his competitors have read the How to Bake 101, Be a Baker 101, baking for dummies. Machine learning has the potential to discover patterns. It has the potential, even in supervised learning, to uncover the relationships between variables much more precisely. Or not precisely, but dynamically. And in any economic setting, any business setting, situations change. And machine learning, key being in the name, has the capacity to respond dynamically to new information. It will make mistakes, but because the mistakes are priced in, it's actually somewhat more efficient in that respect in a highly changeable environment than the alternative, which in this case presumably will be a standard business model with rules. Would a human perform the job better? What do we say when we answer this question? That is a question of opportunity cost. So would it perform better? How long would it take the human? Would it take them 100 years to do this? How much data is there? Could the baker be baking while the machine learning learns? If any question of this nature, you have to unfortunately do the rather sobering analysis. Excuse me, sobering economic opportunity cost analysis, which is to say, how valuable is my time? In all likelihood, a baker with one bakery is not going to produce the volume of data needed to feed into a constructive machine learning algorithm. But suppose he did have scale. The greater you can see, there's a cross. It's the more data there is, the harder it is for the human, the easier it is to machine learning. So volume of data is extremely valuable insight here, a piece of information that we should have when we're making this judgment. And we're going to be doing a few of these, by the way, checkpoints on learning. Although you'll be glad to know that it's almost, there aren't that many. What are the inputs to a system? The inputs to a system here are just those in the question. So a baker, one man or woman, would like to optimize pricing of their cakes, so price, in their bakery, singular. Depending on previous pricing, so we got some data. Cost to make, okay, that could change, and time of year. So we have So we have some static information. We've got previous pricing, so that's a data set. We've got time of year, which is probably paired to previous pricing, and cost to make. And cost to make presumably is responsive to things like inflation. So you could look at cost to make and say that can change. So we can, in a way, we can make our machine learning model, and then we can vary cost to make to work. We can make the machine learning model, and then from that construct a more standard statistical model, and then vary cost to make to see if it's profitable or not. And at that point, you'd be doing your cost minimization exercise, your sort of standard microeconomics cost minimization. We don't have a way actually here to look at. We don't have demand. We have implied demand maybe. We don't have enough to do profit maximization, but we can minimize cost. How could the ML model go wrong? Spoiler, machine learning models can't really go wrong because they don't pretend to be able to do anything. The modesty of machine learning models is really the key to their success. A machine learning model doesn't claim to know the truth of anything. It claims to have seen a correlation. And it claims to have mapped that correlation. It claims to have drawn out some features which may or may not be related, but in this data set, they appear to be related. They were correlated. So the extent to which a machine learning model can go wrong, as I would say, betrays greater expectations of machine learning than are appropriate. But in this setting, you could say go wrong would be I spend hours on it and it does nothing. So that's another question of sort of like opportunity cost. I guess go wrong could also mean that it comes out with bad suggestions. But assuming you've done it correctly, it will come out of the suggestions. It will come out of the suggestions that your data is capable of producing. So that's the fault of the data. Checkpoint on learning. Another one. An ocean conservationist would like to track fish populations over time. You can see immediately that this is going to be a tough one because the ocean conservationist is an expert. So replacing his model is going to be difficult. What about the scenario makes it suitable for ML? The uncertainty. Speaking from my very narrow knowledge of ocean populations and fish generally, I would say that if you were to take a sample of any population in the ocean, you couldn't possibly hope to encapsulate all of the systems. You'd be left with massive uncertainty. And in a sense, machine learning is quite good for uncertainty because as I said, it's a very modest. In a sense, it's very modest in what it promises. It just says we can map this data and hopefully it will correlate in some way. And uncertainty makes it unsuitable for rules. So an ocean conservationist of all his intelligence, maybe just simply attaching too many provisos to his analysis to make it useful. If the sharks come in from the other side of the ocean, if the whales rise up from the deep and eat the fish, a machine learning algorithm can be more, machine learning program can be more sober about those sort of things than an expert. What is the benefit for the organization? Automation, probably. This sort of research is intensive and expensive, which is the third question. Would a human perform the job better? Opportunity cost. Ocean conservationist is an expert. Probably he has expensive time and little of it, and perhaps machine learning algorithm could help him do that. An ocean conservationist intern, on the other hand, actually might be better than the machine learning algorithm because they could devote a lot of time to it. They could bring to bear knowledge, and they could avoid some silly errors. Oh wait, didn't do finals. What are the inputs to the system? Fish populations over time. We could also say ocean conservationist is an input because they're asking us about the performance and the general business model. How could the machine learning model go wrong? Doesn't factor in sharks. Sharks turn up and they eat all the fish. I don't know. So the lack of rules, essentially. An online brand influencer wants a model that can predict the number of likes that a particular post may get. What about the scenario? Make it suitable for ML. So as we discussed previously, this is ideal for ML because social media has such an enormous abundance, multitude of data, and very, very few priors. So it's very difficult to categorize. The categories are evolving constantly, mutating, speciating, dividing, goes flying towards obsolescence, misclassified constantly. It's producing a rule-based system of social media would be frankly impossible. So it's machine learning is really all you're left with. So machine learning for this is ideally suited. Lots of data, very few ways to conceptualize it. What is the benefits for the business or individual? So as I said, the value proposition of these social media giants is that they have this enormous quantity of data, and they have performed operations on it to tease out patterns that might otherwise be invisible to the human eye, but more than that, are so abstract and variegated that human simply can't conceive of them. They're too minuscule, too granular. They're working at a level of abstraction that is simply beyond our comprehension, and that poses all sorts of ethical problems, but that is the essence of deep learning. Would a human perform the job better? No, impossible. There are human suggesters, and in fact, a lot of the AI ethics boils down to human moderation of these patterns. I've yet to see a labor cost efficient way of doing this. What are the inputs to the system? The various different things like likes, number of posts, etc. Anything online, in a sense, could be roped into this. Anything on the platform. How can the machine learning model go wrong? Well, as we discussed, there's an ethics question. It could suggest it could push people towards more and more of the same content, which deprives them of intellectual diversity in a way that could be deleterious to their mental health. But as I think I said, it's the question here is the question becomes how can you evaluate a system that is working at a level of abstraction and granularity that is really almost impossible for us to understand. Nearly impossible. We're talking about trillions of data points. How do you evaluate that except with other machine learning or other algorithms? Okay, so let's move on. And we've beaten that one to death. Create your own scenario. So this is one perhaps you can do at home, but look at these questions and be aware that these are similar to the questions that a manager would ask you if you wanted to introduce machine learning. Okay, and in fact, I'll actually share with you a machine learning project process map, which allows you to sort of look at these questions and then translate them into a business process, which will be explicable to non-technical staff and colleagues. Okay, that's the end of the presentation, which leads us to the fun. This is where the fun begins. Okay. Let us look at the fun time. And for this, we're going to use R or Python. Python or R. I understand that for social scientists, R is more usual. For computer scientists, Python is more usual. Python or Java. There's actually a lot of ways you can, lots of different languages for machine learning. You can use Julia, which is another language used in social science, and has a fast growing machine learning community, which is supporting its various outputs. You can also use Java. There's a very good framework for machine learning inquiry called Waka, I think. It's yeah. Let me check that one. Java is obviously one of the most used languages. It's unfortunately suffering a slight reputational problem, but Weka. That's what it's called, Weka. Sorry, Weka is a flightless bird in New Zealand. I knew it was named for a flightless bird in New Zealand. That's what I knew, but I didn't know specifically its name. I have used it; it's really good, and I think it's good if you want to sort of GUI for your machine learning. So machine learning can often be intimidating because you just have a bunch of scripts. You just write your code and you sort of put it into your own scripts. But Weka has like its own sort of R studio for machine learning operations, which can be kind of reassuring, and there's a lot of documentation around it. And in fact, I think it's from the Waikato environment. Oh yeah, so it's called the Waikato Environment for Knowledge Analysis, and it's developed by the University of Waikato. I'm probably butchering that pronunciation. It's based in New Zealand, and they support the package, and they still do, and they've got a lot of resources online. So those are your options: R, Python, Julia, Java. What else is there? Let me just think quickly. Of course, you can do it in C, C++, C#. These are the kind of like the most powerful languages, most similar to the actual language of computers, so they can achieve the most computational power. And I think a lot of the actual machine learning that's done by professional machine learning engineers will have been done in C. But for our purposes, we don't need that. So let's do R first. R for that long, painful digression. Let's just our studio can boot up. Window, R studio, share. Righty ho. Okay, so let's the way R works is that you have, for those who don't know what R is, it's a statistical programming language. It's not technically a programming language. You're going to be slightly at C, outside your R terminal, your R studio. If you have to venture into the wider computing world, it's not going to be terribly easy. But for statistics, it comes with a lot of inbuilt statistical methods that are very useful, economical for you. Okay, so let's install packages. We'll start with TensorFlow go to Keras. I'm not sure if we actually need TensorFlow. And then some standard statistical packages. Tidyverse is just a way of organizing your data in a way that is standardized, and there are lots of packages to support the tidyverse, the tidy way of doing data. Dplyr, just trying to remember my R here. Magritte, I think that's one. Let's do these first. We could be stuck in doom loop here, which is where it installs and then asks you to restart, and then it tries to install again, prompts you to restart. So we're moving to while it's restarting. Let's get cracking on putting in the new libraries. I'm not sure if there's a way to list libraries. Maybe you can do it like this. Keras, TensorFlow, Tidyverse, Dplyr, Magritte. Oh, it's restarting the session. It's still restarting the session. Let's run it again and actually see if we don't want to restart. Yeah, let's put Y. Let's just say yes. Okay. So we're moving swiftly on to, hopefully this will work. I hope this library, okay, it can't be a list, can it? We don't have dplyr. Okay, well, we'll just remove dplyr. Let's just do this one by one. I mean, maybe we can do it like this. C, create a list function. Okay, wow, it must be a blank one. Okay, so let's do it individually. So now we've got Keras, which is our machine learning library. Okay, it's done. It's done that. It's got Keras. Let's get some data. We're going to use MNIST. MNIST is a data set of tagged clothing items. So it's very useful for supervised learning because you have a huge database of images and tags, paired data. Very useful. And we can get it from database. It comes with Keras. So there we go. Just loading in that data. Might take a while because it's a huge data set. Now, what we want to do is, let me just take you through the steps of this. I think it's done it now. So let's, this is the way I start every single machine learning program I do, okay? Break it down to steps. You want to split your data. You want to build your model. You want to compile your model. You want to fit it, and then predict it, and then evaluate it. So let's, whoopsie daisies. I'm actually going to copy this. This is just a way of like, if you see down here by 11.1, it's just, this is a way of dividing up your R script. So I'm just segmenting it. So now we're going to build model. These are the stages, right? So let's compile it. So compiling will be familiar to anyone who's used a compiled language like Java. Basically just like you write your script and then you compile it into computer language, and then a computer sends it off to be processed and then returns it. So compiling, that's familiar. Should be. If it's not familiar, then don't worry, it doesn't actually matter. It's just a step we have to go through. Fit it and then predict. I'm sorry, I'm getting too many spaces here. That's too many spaces, yeah. And then we're going to predict again. Sorry, we're going to evaluate, and that's done. So here you have your stages, right? I guess this should be like number one, get data. But once you've got your data, these are your stages for doing machine learning. And this would be simpler if we were doing it in Python, but since I know by popular demand that R is more popular in this community, I'm going to do it in R. Get some space. Give me some space, man. Once you know these 6 steps, you're basically on the home stretch. Well, actually, that's a lie. But you've got your data, you've got your steps. Just try your data, and imagine actually when people say split data, it's sort of misleading, because what you imagine in your mind is it's split in 2, but it's really split in 3. So you're going to have your X and Y, and then you're going to have your test and train. So if you imagine like a 2 by 2. Okay, so let's do our data is called MNIST. So MNIST, I'm going to train it. I'm going to train it on X. Train X, and we've got to get this from somewhere, unfortunately. No, sorry, we've got to alter it slightly, make it more palatable to us. Train, just doing the exact same thing. So just look at the pattern here. You're going to want to be doing a lot of pattern matching. I've put it as 255 divided by 255, just as a way of making it more palatable to us. Now we're going to want to do a test on the same X. So test. Yeah, that's right. X. Whoopsie daisies. X. And then MNIST. Sorry. It'd help if I could type, wouldn't it? MNIST. Train. And then X. Oh, whoops, sorry, that's not meant to be train. It's meant to be test. Just look at the patterns here. You don't have to understand everything. Just try and get a sense of the steps. Okay, so we're going to run this now, and hopefully it goes through. All good, all good. So we split our data. So the first, we got an X and Y, and now we split it up into train and test. So we've made progress. So now let's build our model. Okay. Let's think. Model. Doing a quick shortcut. No, there's nothing to do it yet. We're going to do a sequential model. Model sequential. Again, you don't need to be desperately aware of this. I'm just adding a pipe function there. Hopefully, we've added a magritter or dplyr, because that's what uses this pipe kind of thing. Right. We want to create the layers of our. If you remember last time, we used the TensorFlow playground. And if you just imagine the layers, so there was like an input layer, then hidden layer, another layer, and then you had your output. Okay. So what we're going to do is we're going to build those layers. And this is entirely kind of up to you, but this is the way that I'm going to do it. Okay, I'm going to flatten it first. Fits here. LSTM. LSHTM. No. Lame dad level joke. Okay. Input. Whoops. We meant to be. So we got to decide what shape it's going to be, and we're going to go for the shape that's the square shape. If you're wondering what I'm doing here with this piping, this is just another way of laying out like a function in R. And the shortcut is Shift Command M. So I'm doing it so quickly rather than doing like percentage sign greater than percentage sign. Gotta add another layer. It's a dense one this time. These are like the hidden layers. Maybe we should read this with documentation because that might be helpful to us. Just asked up top. Dense. So okay, no, this is just like formatting. So we're just going to specify the units in activation. The object is actually implied. Okay. I think it's. What it is. 128. I think is the that's you couldn't know that, you can't deduce 128. It's just from this data set. An arbitrary number. Activation. Now here's our old friend. Okay, you remember ReLU, don't you, from our previous machine learning exploration. You know what's craziness? I'm going to actually look at one of our old lectures, and you can actually see the explanation for ReLU. Oh man, come on. Don't do this to me. I think the neural network, we're of course making a neural network, so this is all of a piece, okay? I'm going to present this, then going back here, I'm going to stop sharing this for a second. Share screen again. Hopefully this works. I mean, it works in very mysterious ways. Yeah. Okay. You're seeing this. Let's go to our old friend, ReLU. Rectified linear unit. Activation function often works a little better than a smooth function like a sigmoid, while also being significantly easier to compute. So because we're running a huge data set, we want it to be easy to compute. But moreover, if you look at that straight line, as you can see, we're just trying to get that. We're just going to try to get a value over 0. Otherwise discounted. But here's what we're doing. These are the layers, guys. These are the layers. This is like the visual representation of what we're doing right now. So I'd revisit this as a way of kind of like clarifying. We've been through that, but bear in mind this. Yeah. Features. Hidden layers. We're building the layers now. We're going to output soon. Here's a very similar operation, okay? What we've got are images of clothes. That's what MNIST is. And we've got tags. Here you had images of dogs or cats, and you had some tagged, and then you were trying to find out whether these images, which have been fed into it as inputs, are either one. In this case, Labrador Retriever. We're using ReLU. So put this in your mind, ReLU. Now back to our script. Okay, window, RStudio, chat. Boom. Okay, so we've got ReLU. We want another pipe. This might not work. I'm doing this from kind of memory. So, what do we need now? We need the drop. There's a lot we could add here, by the way. This is a very subjective way of doing it. Drop. Yeah, drop. Again, don't worry about this number for now. What we're trying to prove is that what I'm trying to show you is the implementation of what we've been learning. We're going to do another layer dense probably. We could do another. Yeah, let's do another layer dense. Mm-hmm. 10. Activation. So this is just what we did before. Activation, softmax this time. And hopefully that works. This is okay. This is not an error. What we have here is not an error. It's just telling us how it's doing the computation. Not a problem. Let's look at the model. If it's worked, then we'll be able to actually see it. Here it is. Total parameters 101,770. Trainable parameters 101,770. Non-trainable parameters 0. Good. That's good. I think these are the values we want. Actually, we could have done summary. That would have been cleaner. Yeah. And there we go. Now we're going to compile this thing, which means we've got to put it into action, and then when we fit it, that will be when we actually properly run it, so you can see the loss. Okay, model compile. So we're just doing this on model. Compile. Loss. We'll decide how we're going to do the loss. We're going to do sparse entropy. Don't have to worry about this for now. It's just a way of doing loss. It's just a way. It's like drawing a line. It's related to that. Okay. Optimizer. This is how it iterates. We just do standard atom, and then finally, hold on. Apologies. Let's just. Okay. I think what we want to do here is metrics. So this is just standard. What we saw before was measuring for accuracy. That's what you're generally going to want to be doing. And hopefully this. Okay, actually no. I'm sorry, I made a mistake there. Categorical. error. Sparse categorical entropy. Yeah, I think this is correct. No problems. So now is the big one. So we're gonna go back to our model. This is where we kind of we do the running, and we pray it works. This is when we do fit. So let's do it. Sorry, I accidentally added an object there. So now we're going to take our data and we're going to fit our X data onto our Y. Okay. So now we've done the X spacing test, training and test. Now we use Y. Let's sorry, yeah, MNIST train. This is what we did before. X, and then our Y is going to be. Sorry, it would help if I could type correctly, wouldn't it? It's also going to be training. If I remembered how to use my keyboard, also be very helpful. Y, and then let's do that. Epochs. You remember epochs? That's what we used in the TensorFlow playground, just to like how many times to do it. So this is just length of the program. We're going to just do 5 for now. We'll do validation. I think validation split equals 0.3, and you don't have to worry about this. It's not within the scope of the course. And hopefully this will now give us a. This will now allow us to run our model. God willing. God willing. Yeah. So you can see here on the right, it is doing it. It's now running it and it's iteratively improving it. So you see it's minimizing the loss. It's improving. It's driving down loss. This is just what we saw in the playground application. It's trying to get down loss. I think it's reached its, yeah. Okay, so we've done five epochs. Just for the sake of it, let's just do 30, just see how it goes. We're going to push our computer a bit computationally. See how it gets on. Right, so loss is being driven down. We'll go more into depth into interpreting this at a later date, but it's important for you to be able to see that based on some data, which, by the way, the MNIST is just images with tags. Jumper, word jumper, it's just that simple. It's a boot and the word boot. And then we just feed some more images to it, which is what we've done here, and we're training this data. We're running this machine learning on it. Hopefully you can kind of see this. It's useful to kind of see it to have it kind of visually in your mind, because then when we go to do this at a later date, you can sort of visualize what we're attempting to do. So it's got down to 23, 24. It's plateauing. It's plateauing. I think accuracy is it's reaching the maybe it's beating my expectations. Frankly, there's nothing mysterious left about this data set. It's been so experimented on. But we ran 30 epochs, and we got to a loss of 0.0165. Not too shabby. Not too bad. Not too bad at all. What could we change? We could change the loss. We could change the optimizer. We could change the activation. On this occasion, we're not going to do that, but I think this is demonstrated, and indeed we won't do Python this time either, I think. But it's been useful for us to demonstrate how we could change it. I mean, let's just do one thing. I mean, this might break the model, but let's try 0.1. Just playing around, just messing around here. Remember, the high score to beat is 0.0165. Watch it go. Disappointed so far? All right, well, I'll give it a few more seconds. I don't think it needs to go to 30 because it's clearly sort of plateauing. Oh, we're about the same value, 0. Okay, we've got a new low score, 0.015. So clearly the validation split. We could do 90, 90, 10. All right. So now we get to our final step, which is predict. Just did every project, but and then evaluate. Sorry, so it's penultimate. Let's put this back to 3, just so it doesn't take such a long time. But now we're going to make our predictions. So we're going to create predictions variable. You can see I've already created something called predictions previously in my R. But we'll do it again. So now we just input model into predict, and we'll use the data we'll use is the MNIST, obviously. Test X. Yeah. And that's it. That's all you need to do for the predictions. And then we'll create. Then we can actually see what our prediction. Okay, that's not very good. Let's do summary. Oopsie daisies. Summary. Okie dokie. So we've got some summary statistics here. Oh, maybe what should we? Okay. Maybe it'd be more useful if we did head actually, just to like see, because we don't need these summary statistics. What we need is just some values. Here we have some values. First few values. First few rows. Sorry. And these are our predictions using the test data. So from our model, we've built a model, and now we've just tested it, and these are our predictions from that test data. Finally, evaluate. Similarly, what you're going to see here is, and what I want you to take away from this is just pattern match. Okay, so a lot of what we're doing is we're just doing operations on model. So that was what fit was, that was what compile was, that was what we built the model, and then compile and fit and evaluate are all just operations on the model. So evaluate, unsurprisingly. Nest, we could just copy, actually, let's just copy this from this. Of course, we can't use train. We're going to evaluate it based on X and Y, of course, to get a complete understanding. Yeah. And then verbose, of course. Don't worry about what verbose means at the moment. Have I made an error there? No. So here we have our final loss. So that's not quite where we ended it on previously, but it's an average. So our accuracy was 0.98, pretty good. Loss 0.124. So if you ran that if you were able to predict that accurately with anything in your work, you'd be happy chappy. I suppose they're very good values, and it means that you were able to accurately predict 98% of the time. So that's jolly good. And I hope this has been this has provided a short demonstration to you on how we construct these models. So what we're going to do in the future is we're going to do ad nauseam. We're just going to do split, build model, compile, fit, predict, evaluate. We're going to get various data. We're going to split it up as we do machine learning. We'll build a model from it. We'll compile, fit, predict, and evaluate. And that's it. So you run your first model. If you run this, you run your first model. And it's important to look at this and see that you are indeed making something. You are running something, and you can visualize it. This is all contained. This, of course, all is a simplified version. We haven't done any maths here, for instance, and that's because we're drawing from the TensorFlow Keras API. So the backend is essentially all being done by Keras TensorFlow. What we have here is we're being able to take data, which we have, in this case, standardized data, and feed it into this API, and with these instructions, and we get a rather good result. And provided you could structure something like this, and remember, it's just paired data, okay? Just paired data. That's it. Photo of cat, cat. That's it. That's all we've used. That's it. That's how simple this is. And we've been able to train it so it's 98% correct. Now, admittedly, we had a lot of values, but this was image classification. Okay, MNIST is image, and what we were able to do, I think, is almost proof of concept. The difficult bit going forward will be the first step, getting your data in working order, and secondly, learning all of these different kind of contingencies. But the bones are there. Build your model. You just need to split your data, get your data, split it, compile it, fit it, predict it, and then evaluate it. You'll see different iterations of this sort of pattern everywhere. If you're interested to start with Python, I would recommend Kaggle. Go to their machine learning pathway, and you'll see something very similar to this. Slightly different because they do it slightly differently, and they use something called scikit-learn. But the basic ideas are much the same. TensorFlow is in fact slightly more advanced. But thank you very much. We're an hour and a half in, and I think this has been an excellent tutorial. And thank you so much for coming. Stay tuned for more. We're going to do another one of these in 2 weeks, and I feel that would be even better. We can do even more practical machine learning. Okay, I'm going to stop recording.